Yeah, it's my pleasure to welcome Karlee Westrem from Michigan Technological University, and she'll talk today about a new symmetric function identity with an application to symmetric group character values.
Thank you, and thank you for the invitation to come here and speak, and for all of you for being here. So yeah, as it was already said, I'll be talking about a symmetric function identity and then its application to symmetric group character values. So we will go over some partition theory background, character values, symmetric functions, and then I'll talk about the identity that I proved, and then its application to the character values of the symmetric group. So starting off with partition theory, we'll recall a few definitions. So lambda will be a partition of n, denoted lambda 1 through lambda r, so r parts. If we have a weakly decreasing parts, and they're all positive integers, and all of the parts sum to n. So that will be a partition of n. So for example, if we look at the partitions of 5, we have 5, we have 4, 1, 3, 2, 3, 1, 1, all the way down to 1 to the 5th, or 1 5 times. So those are the partitions of 5. Other notations that we will talk about will be the size of the partition. So before it was defined as n with the absolute values of lambda. And then the number of parts will be also called the length sometimes. It'll be L of lambda. Then our cal p here will be the set of all partitions, and p of n will count the number of partitions of size n. So for our example, partitions of 5, we have 7 of them, so p of 5 is 7. Okay, so coming back to lambda is lambda 1 through lambda r. Tewodros introduced these two sets. One we'll see later on, but the first one was EV of lambda, and it's the set of all partitions from our original lambda given. And for each part of that, we're either going to double that part to lambda I, or we're going to make 2 copies of it, lambda I, and create a new partition, and we'll rewrite it in decreasing order. So it is a partition by definition. So this set of partitions will have 2 to the number of parts elements, where each partition is now partition of 2n, since we're doubling or copying each part. So for example, if we had lambda is 3, 2, 1, then we can build EV of lambda in this way. So we have 3 parts, so we have 2 to the 3rd number of elements, so 8 partitions here. And notice here we're either doubling 3, 2, 1 or making 2 copies of that. So this is EV of lambda. Another example, 2, 2, 1, 1. So now lambda has some repeated parts in there. And for EV of lambda, we have some partitions that show up more than once. So they're denoted on top there by ×2 or ×4. So we have some repeated ones in there, so not distinct. Teddy also defined 2 other subsets of partitions of size m by making a restriction. So either on the rows or the columns, and to be of even length. So they're denoted in this way. We have r sub n, capital N, of m, which will be our size. So we're taking partitions of size m, and we're restricting the number of parts by this capital N. So we have a couple parameters here. And for r sub n of m, that means every row has to be of even length. Now, if we add a c on the top there, we're referring to the columns being of even length there. So we have 2 other subsets of partitions. For example, if we had capital N is 3, and we're looking at partitions of 8, size 8, then R3 of 8 would be these 4 partitions here. Again, at most 3 parts. And R3C of 8 would just be 1, because we could have at most 3 rows. We want the columns to be of even length, so we only get 4 here. Okay, so we'll put that aside for now, a little bit partition theory, and we'll come over to the characters of the symmetric group now. So now we're talking about irreducible characters that show up in the character table. Now these are labeled by partitions as well, and the conjugacy classes are also labeled by partitions of n via their cycle type. So we're still working a little bit in partition theory here. So we have chi of mu sub lambda is our irreducible character of mu on the conjugacy class lambda. Again, talking in the symmetric group here. Now, one can calculate this character of the symmetric group by using the Murnigan-Nakayama rule. Sure. But for this specific project, we look at it in a different light. So we're actually going to look at it as a certain inner product of symmetric polynomials. So we're going to sidestep that rule and see if we can find out some information looking at this inner product of symmetric functions. So before we do that, let's look at symmetric functions. So we come back, lambda is a partition of n, and we have a few different symmetric functions that we're going to use. Monomial will be the first one, and lambda. And it's defined in this way. So essentially we're summing over distinct permutations, alpha, given that partition lambda of n, and we have an infinite number of variables, x1, x2, etc. But all you need to know is kind of how they work. So we have M11 is this power sum xi, xj, where I is less than j here. So xi to the first, xj to the first. Or if we have M21, we have xi squared, xj, where those are not equal there. So anytime we think of monomial functions, I want you to think of something like this, these examples here. Next up, our second set of symmetric functions will be the power sums, which will be related to the monomials in this way. So P sub n is equal to m sub n, and it's our sum of x sub I to the n. So we have the power sums there, when n is a number greater than or equal to 1. So if we take our partition lambda with whatever number of parts, P lambda is the multiplication of P sub each part there. So P sub lambda 1 times P sub lambda 2, etc. So we're going to use this definition once we talk about the application to the character values. So for example, a concrete example, lambda equals 321. P sub 321 could be written as P3, P2, P1, or we could translate it to our m's, M3, M2, M1. Our final one that we'll talk about is the Schur polynomials. So S sub lambda. And now these could be defined as monomials where we're summing over semi-standard Young tableau of shape lambda, denoted by T there. So the exponents are given by the weight. If we look at an example, lambda equals 2, 1, where we restrict it to 3 variables in this case for this example, just to write it out here. S sub lambda 2, 1 with 3 variables is given as so. So here's where the semi-standard Young tableau come in. They're weakly decreasing across the rows, strictly increasing as we go down the columns. We have our summation with our x terms. So you can see there, for the last one, we have a coefficient of 2 there. So those, oh, go ahead.
Yeah, so these give you the characters for the reduce for the general equality.
Yeah. All right, so those are our 3 symmetric functions we are going to talk about: monomial, power sum, and Schur polynomials. And we have a way to get between the symmetric functions as well. So one of them that comes up is Young's rule, expressing Schur polynomials or Schur functions as a linear combination of monomial symmetric functions. So there's a lot of ways to go in between these bases of symmetric functions. Okay, so how does this relate to the character? Well, in Stanley's book is one location of this statement here, probably can find it other places as well, but it says that the character of mu sub lambda is the inner product of p sub lambda with the Schur polynomial s mu here. And so when looking at this, our goal is to calculate this by turning this p sub lambda into s's if possible. So let's do that. So p lambda could be written as the sum of monomials, m's, and we can use this definition with the inverse Koska numbers in this fashion. So m sub lambda can be written as a sum with the inverse Koska number there. And applying that, which will be a little careful when we actually do the calculations, but you get the idea of what's happening here. We start with p's, we transfer to m's, and then somehow we can transfer to s's is kind of the goal here. But like I said, we do need to be careful because if this m lambda has multiple parts in there, we can see what happens here with specifically two parts. So if m lambda had two parts, say lambda 1 and lambda 2, when we do this multiplication in the second step here, we have something happening like this. We have the Koska, inverse Koska number twice. And then when we multiply that through, essentially what we're keeping track of is the two inverse Koska numbers. But then when we multiply the Schur polynomials, something else pops out. And that's the Littlewood-Richardson coefficient as well. So we have to keep track of these coefficients as we're multiplying the m's. So that's something to keep in mind in this calculation here, is that we have a few coefficients that linger through as well. So it becomes quite complicated if we have more than two parts. But the great part is, if we can do this, if we can figure out what that coefficient is, the s's form an orthonormal basis. So if we can get the two parts in terms of Schur polynomials or Schur functions, then we can calculate it directly by just pulling out those coefficients that tagged along, especially in this example described here. So now you get the idea of where we're headed with this type of calculation. So as I already said out loud, goal is to calculate first, how can we make that transition from p lambda to Schur functions, keeping track of those coefficients in front. So that's where I started. I got a little detoured as we went through, and I found this symmetric function identity along the way. So I'll kind of explain a little bit where this came from, but essentially what this says is that we have some lambda with r parts, a partition of n, and I have this alternating sum of p lambdas, where the p lambdas are actually coming from that EV set that I originally defined. So p lambda tilde is what we're working with here. So somehow, if I take the sum of these p lambda tildes and I attach their sign to it with their length, I have some type of cancellation happening. And all I'm left with is the product of these monomials of that form, m sub lambda I, and I have this extra factor of 2 to the r, where r is the number of parts. So it's pretty fascinating to see all of these terms that happen, and it cancels down to exactly one term here. All right. So here, an example illustrating the identity. So suppose lambda is the partition 2, 1. EV of lambda will have 4 elements, 4, 2, 4, 1, 1, 2, 2, 2, 2, 2, 1, 1 here. So looking at that left-hand side of the main result, we're looking at p sub lambda tilde attached with its sign. So the number of parts is this exponent here. So we have p42 minus p411, since it has 3 parts to it, and that's why we also have a negative in front of the p222. So we can convert that to our monomial functions. So our first one here, M4, M2 comes from the first part, and then we have the other terms as so from each one. And then we can expand it further there. So we have the multiplication of monomial functions expanded out completely, and we see the cancellation happening directly here. So the only terms left will come from P or M sub 2, M sub 1, with 4 copies of each one here. So let's look at the proof here, illustrating what's happening. So when we have this summation, this alternating sum of 2 to the r elements, essentially what's happening when we make that expansion is that we're making choices. And those choices are for each part, for the m's or the p's, whatever one you're writing in first, is that we either have p sub 2 lambda 1 or 2 copies of it. And we do that for each part of lambda, so through lambda r. There, so we're either doubling each part or making 2 copies here. So those are our choices from the start. Now the goal is to track how are these cancellations happening when there's a large number of them occurring. So essentially what we can do is say, okay, we have a monomial. It's going to look something like this. We have our x variable with some subscript, and we have our exponents there. So this is the most expanded one. Notice here the first two, x1, j1, have the exponent lambda 1, and so on, lambda 2. And of course, if along the way we would have made the choice of p sub 2 lambda k, then in this monomial we see here, that would mean those 2 parts would come together and be 1 there. So x sub k would equal j sub k. So essentially we're looking at these monomials here, and when are we combining them, and how does that affect the sign in front of that? So again, if the choice was the opposite thing, p sub lambda k, 2 copies of that, we could have choices. At some point we could combine them or not combine them. Okay, so now we look at the coefficients. How are these monomials canceling in the expansion? So we denote t to be the number of positions where we decide we make that choice of using p sub 2 lambda s or k, or t in this case. So we're looking at the number of times we do that in the monomial, combining those together. But for that to happen, it could have been the case that maybe our original choice was having 2 copies, or maybe our original choice was having the doubling effect. So essentially we're looking at the base case and how can we combine these together? Now we could do this for any of these positions as we go along for any of the R parts. And then of course the others would have the opposite, right? They would already be combined there. So again, the other ones wouldn't be combined, meaning that those subscripts could not be equal. And essentially we would have a choice, either having x sub is first or j sub s first from that term there. So we have two possibilities there. And what this means is that if we're counting these coefficients of choices that we make, we're going to have this alternating sum. T choose 0, so the number of positions that are equal is 0. We could have 1 that's equal, but it would give a minus sign in front of that monomial. 2 all the way up to t choose t here. And that sum should look familiar, and it does equal 0 here. So we have this cancellation happening and our extra 2 to the r minus t coming out front, which doesn't make a difference there. And the nice part is if t is equal to 0, then we have 2 to the r for that simplification happening. So if t is 0, simplifies down to 2 to the r. So again, the only one that's left is that t equals 0 case. We have that one monomial that's expanded completely that didn't get canceled out. And it's equal to the product of this M, so lambda I there. Okay, so how does this apply to the characters of the symmetric group? So there was a conjecture that Teddy shared with me, which was kind of the original start point. But we kind of backtracked and looked at it in various lights. But essentially what he wanted us to look at was this character that we've just been talking about in terms of symmetric functions with the sign attached. And we have some conditions on mu and lambda tilde. Lambda tilde, just as before, comes from EV of lambda. And then this is where this other set that we originally defined comes into play, mu. So we have some restrictions on mu. The number of parts on the left-hand side can be at most 2 times capital N plus 1. So could be odd number of rows there. And of size, 2 times the size of lambda. In this case would be n. So this would be of size 2n. So we have partitions with at most 2n plus 1 number of rows and of size 2 times small n there. And what we were finding for small examples that sum with the sign attached is equal to this other character value with no sign. And now we're looking at partitions with even columns. So very strange character values summing together, one with an alternating sign, one without. So this was kind of the original starting place. Okay, so let's look at an example of how this kind of plays out. So if lambda is 2 to the second, comma 1, or 2 to 1, then as described here, we have a couple repeated partitions in here for EV of lambda. And we can write out, if we don't have any small restriction on capital N, the number of parts, then we have these partitions here. So we're talking about partitions of 10, which is 2 times 5, 2 plus 2 plus 1. And here is kind of our playground where we're coming from, what we'll be working with. So let's look at the partial character table and see what's happening here. So we see our elements from EV lambda and those partitions that we saw for the even rows. So Rn of 10. And here's the character table. So the character values from there. And what we were saying was that we have a sign attached. And also for some of our partitions here, we also have a few repeated as well for that. So we have to keep that in mind that we might have some repeated here. So there's our character values. There's our signs and also the 2's, since we have those 2 columns repeated. And I also put on there the row sum. So if we sum across those rows, we get zeros and sometimes minus 16. So the binomial coefficients that appear and the signs in our sum. Okay, I also attached here kind of how this breaks down. So if capital N is 1, in the smallest case, we'd be summing the first 4 rows here because we were looking at 2 times capital N plus 1. So 2n plus 1 would be 3 parts, at most 3 parts. So that would be these, first 5 here, first 5 here. And then if n grows a bit larger, so 2, 3, 4, 5 to get the rest of them, we would have the full sum here, so minus 48 there. So let's see how that works out. On the other side, so this second chart here, we have the same thing on the top. We have now even columns, but now we don't have a sign. We just have the binomial coefficients popping up. And we have these numbers again appearing, but in different orders. So for the first one, we're looking at 2 capital N. So at most 2 parts, or at most 4 parts, 6 parts, etc. And so with these calculations, we see for capital N equals 1, we're restricted to 3 parts on the left-hand side. On the right-hand side, we're restricted to at most 2 parts because we had 2 capital N, and their characters sum to -16. For the other ones, in this small case, we would get every other partition and we get -48. So it works out. Now, let's look at a bigger example. So I won't show you the character table because it would fill up the whole page, but we can get the idea of it. We have higher binomial coefficients happening in here that we have to keep track of. And with our calculation, even the smallest one, n equals 1, they both sum to 224. So somehow these cancellations happen and we get 224. N equals 2, we go up to 2,176, and so on. And then if n is greater than or equal to 4, we get the remainder of the partitions. So the part sizes are small enough where we capture everything at that point. But still not clear, even with that sign cancellation, how these two sets are equal. But we were able to notice something looking at those partial character tables, that if mu1, so of even length, as described, is greater than n, half the size of the partition, then those character values are 0, which is what we saw before. So let me click back to that. So we see that here. So 10 is greater than 5, greater than 5 here is 8, same thing here, and same thing here. So the largest part size was bigger than n equals, small n equals 5, and so we get 0. So that was our first result that we saw, was that was the case for that left-hand side. So with that sign in there, if the first part was bigger than n, we didn't even have to worry about those ones there. So we could restrict a little bit on the conjecture there. But kind of looking at the future direction is proving essentially the conjecture, but even small examples, even the capital N equals 1 case is a lot in terms of the inner products, as you saw with those inverse Koska numbers, the Littlewood-Richardson coefficient coming into play. There's a lot of things that pop out when looking at it in terms of the inner product of Schur functions there. So that's currently what I'm working on now, is those small values. Is there a way we can show that for small examples? But other things we've thought about is there any other identities in terms of symmetric functions that we haven't thought about? Do we have to go back to the Murnaghan-Nakayama rule to calculate these characters to show some type of equality for these sums of characters here? And with that, I will say thank you.
The speaker?
Yeah, I have one.
Yeah.
So how much of this can be sort of extended to Heck algebras of type A? Like Arun his thesis actually, computed characters for the Heck algebras of type A.
We haven't looked at that.
It would be interesting maybe to see how these, what the formulation of these conjectures are.
Right.
You have lots of cues around.
Yeah. Yeah, we'll definitely take a look at that. Yeah.
Not really a coherent question, but this set as the lambda where you're either doubling or duplicating.
Copying, yeah.
Hard, why is that showing up? That's it seems like a weird condition to work with.
We actually didn't talk to Teddy about that specifically. It was initially just sharing this results that he had or ideas that he had, but he never told us why EV of lambda with the even doubling or copying. But even with the identity that I showed, there's some even you need 2 to the R or whatever for that, because it doesn't work for 3 or so on, since you don't have that nice cancellation happening. yeah, it's very interesting, for sure.
Can you turn back to 18, slide 18?
Yeah.
Okay, here, does it matter if T is even or odd that you get 0?
No, it doesn't matter.
This is the expansion of 1 minus 1 to T.
Oh, yeah, okay. Yeah.
So general question.
Yeah.
It's an interesting but odd combinatorial identity. Is there
Yeah.
any representation theoretic reason why it should be true or motivation for it or like a different way of thinking about it?
Not yet.
Okay.
It feels very reminiscent of like, so there's this stuff that we do where you like almost if you take two equal parts and replace them by one thing of double length, and that gives you like an equivalence relation on partitions. That describes the blocks in the two modular representation theory. Or not blocks, sorry, it describes, I'm doing that's orthogonal. It describes the basically when two columns of the character table are congruent on two. Is that relation. And so it feels like there's some sort of two modular thing going on, right? I don't
Yeah,
think they're
right.
making a statement. Other questions?
Let's thank the speaker again.
Thank you.